اي جمال. it's 2:30, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? Doing good, I hope. Tired, I bet. That's good. That's good. Yeah, it's late in the semester, so I know you guys must be really tired, especially with everything with the pandemic and staying home and stuff. This is I mean we've been at this for over a year now, but it doesn't make it any easier. In fact, I think at this point, this is kind of the hardest that we've kind of had to deal with this, just because we've been at this for so long. It's all just so kind of exhausting to be virtual and have to deal with all the inconveniences with that. But just hang in there, guys. We're almost at the end. Okay, so today we are going to finish up our lecture notes on heat exchangers, and so we have a little bit more to go. And so I have a couple examples to do for you guys, and also just a little bit more conceptual stuff. All right, so we'll finish that up. Another announcement I want to make is that homework 6 is posted, and that's going to be due on Monday, right? So that's going to be Monday at 11:59, and that's going to cover basically heat exchangers and free convection, right? And so that's all stuff that's going to be covered in the midterm. And so I know the homework due date is pretty close to the midterm date, but think of it as if you can do the homework and and still have that kind of fresh in your mind for the midterm, that's good studying right there. Okay. And so homework 5, I'm just starting to grade right now, and so I'm hoping to finish that by sometime tonight. And then once I finish grading homework 5, I'll post the solutions for that, so you can have that available to study. And then homework 6, I'll post the solutions basically right after the due date, so you can have that to study as well. Okay. One more announcement I want to make is that if you've already downloaded the convection summary handout, and so that kind of formatted handout that I gave you guys to summarize all the convection stuff, I did notice that one thing was missing from it, and so there was nothing on there for free convection for horizontal surfaces. And so that was kind of one of the last things that we went over for free convection. And so I've added that to the convection summary handout, and I've uploaded that onto Canvas. And so if you download it again, you'll see that there's a little bit extra at the end there just to kind of help you out with that stuff. And so I don't think I gave you any homework for free convection for horizontal surfaces, but it would definitely be something good to know for the midterm. Okay, so are there any questions I can answer before we get started for today? All right, okay, so let's go ahead and continue on. Right, and so where we left off last time was actually right in the middle of an example. So actually, let me write out the problem statement for the example again, and then we'll pick up where we left off. Okay. All right. And so in this example, we're looking at a heat exchanger, and in particular, a counterflow heat exchanger. Right? Okay. And the purpose of this heat exchanger is to cool some lubricating oil. Okay. All right. And so schematically, it looks like this. And so we have our concentric tube, and so we have a big outer tube and a smaller inner tube, okay? In the inner tube, we have our cooling water, and in the outer tube, we have our oil, okay? And so since it's counterflow, we can say the oil is going from left to right, okay? While the water on the inner tube is going the other direction. So we'll say the water is going from right to left. Let's put some numbers on this. And so let's say that the inner diameter here, di, okay, we'll say that di is 25 millimeters. Okay. Meanwhile, do is the outer diameter. We can say that do is 45 millimeters. Okay. And we also know the inlet temperatures for the two fluids. Right? And so we have the inlet temperature for the water. This is starting at 30 degrees C. Meanwhile, the inlet temperature of the oil, we're going to say it's going to start at 100 degrees C. Okay. All right. We know the mass flow rates, and so the mass flow rate of water is going to be 0.2 kilograms per second. And the mass flow rate of oil will be 0.1 kilograms per second. Okay. Let's see. And then the last thing we know is that we want to design this heat exchanger such that the outlet temperature of the oil is 60 degrees C. Okay. Okay. And the last and basically the last variable that that hasn't been given yet is the length of the heat exchanger. Okay. Oops.
Professor,
Yep.
for the diameter, is that 25 meters or 25
Oh,
millimeters?
sorry. It should be 25 millimeters. Yes.
Right.
That would be a gigantic heat exchanger, 25 meters. Okay. And so we just started this example last time, and so we didn't get to finish it. And so I think the place where we left off was we just computed the Reynolds number. Okay. Because the way that we're going to approach this problem is that we need to find kind of the total convection resistance between the two fluids. And so to do that, we need to find the convection coefficient for the inner flow and the outer flow. Right? And so we started our process. And so where we left off is basically right after we specified the Reynolds number. Okay? And so I'm going to pick that up on the next page. All right. And so any questions on this so far?
Just real quick question. The M dot, what does that mean again specifically?
M dot is mass flow rate, and so that's basically that's basically the amount of mass that's entering into the for the water and for the oil for each of those. How much mass is passing through per second?
Got you. And then for the millimeters, is it like, so say they give us a problem that says centimeters, do you want us to automatically go to millimeters, or it just depends on the problem?
For this one, I gave it to in millimeters just because that's just the problem. But usually what I like to do for the units is I convert everything to kind of a standard meters, and I do my calculation on that. Yeah.
Gotcha. Okay, just double checking.
Yeah, so I personally don't have a preference as long as you're using the same process and you're getting the right answer. But for me, just to help stay organized, I convert everything to meters, and do all the calculations on that.
Gotcha. Okay, thank you.
Mm-hmm. Okay, and so where we left off was we were finding the Reynolds numbers. Right? And we need two of them because we need the Reynolds number for the water flow on the inside and for the oil flow on the outside. And so I'm not going to run through the calculations again because you can check out the previous lecture for that. But what we found for the Reynolds number for the oil was that it was 56.0. Okay. And for the water, we found that the Reynolds number was 14,050. Okay. Right. And now that we know the Reynolds number, we can select the appropriate Nusselt number correlation. All right. And so let's start with the oil. Since oil is in the outer tube for this heat exchanger, we know that the flow geometry for this is flow in an annulus. Okay. And since the Reynolds number was so low, we have laminar flow. Okay. And so the way that we're going to obtain the Nusselt number is from that table that I showed you on the previous page. Okay. Okay. And remember, to use that table, you have to take the ratio of the inner diameter and the outer diameter. And so for this case, we have di minus or divided by do, and we get a ratio of 0.56. Okay. And so if we look this up on the table, what we find is that the Nusselt number should be 5.74. Okay. All right. And so that's good. And so now we need the Nusselt number for the water in the pipe. Okay. And in particular, since our Reynolds number is so high for the water, we need the Nusselt number correlation for turbulent flow in an internal pipe. Right, and so the Nusselt number correlation for this is 0.023. Reynolds number to the 4/5 times Prandtl number to the 0.4. Okay. And then what we get from that after plugging in the numbers is we get a Nusselt number of 90. Okay. All right. And so this is nice because we know that once we have the Nusselt numbers, we can use these to compute the convection coefficients. Okay. And we need to find one for the oil and one for the water. Okay. And so to find the convection coefficient for the oil, we're going to take the Nusselt number on the inside. And so that's going to be 5.74. Okay. And we're going to multiply it by the thermal conductivity divided by the hydraulic diameter. Okay. Okay. Remember, the hydraulic diameter of an annulus is just the difference between the outer diameter and the inner one. Okay. And so if we plug in all the values for this, then what we get is a convection coefficient of 39.6 watts per meter squared K. All right. All right, and so for the water, we're going to do the same thing. And so we're going to take our Nusselt number, which is 90, and then multiply it by the thermal conductivity for water divided by the inner diameter, okay, because it's the water is just going inside that inner tube, okay, and we plug in the numbers for that, and we get 2,250 watts per meter square K. Okay. Right. And so now that we have these convection coefficients, we can use this to compute the total resistance, total thermal resistance of the heat going from the oil to the water. Okay, and we'll do that on the next page. Okay, so any questions on this so far?
For the oil, that diameter, is it the difference, or is it the entire diameter?
Yeah, so this DH right here, this is our hydraulic diameter, right? And so because normally an annulus is a donut, right? And so you have an inner diameter here and an outer diameter, DO. And so DH is just the difference in between the two. So we have DO minus DI. That's just kind of the standard whenever you're working with an annulus, is to use that hydraulic diameter.
I see. Thank you.
Mm-hmm. All right, any other questions on this page? Okay. All right, and so now what we can do at this point is we can compute the total resistance, or at least get an expression for that. Okay. And so we won't be able to solve for all of it because we don't have the length, but at the very least, we can get an expression for that, right? So our total here, and in this case, we're going to be ignoring the conduction resistance for the pipe in between, right? And so the total resistance is just going to be the convection resistance of the two fluids. Right? And so we're going to have 1 over H oil times A plus 1 over H water times A, okay? Where this A right here, this A is the surface area of the pipe that separates between the two fluids. Okay. And so in particular, that surface area is just going to be the perimeter of that pipe. It's going to be pi di times L, okay? Well, remember, L is our unknown. L is ultimately what we want to solve for. And so we won't be able to compute this yet, but let's kind of stash this in the back of our minds, so that we can come back to it later, okay? And so if we plug in this area here, what we get is our total is equal to 1 divided by pi di L times 1 over H oil plus 1 over H water. Okay. And so I don't have the things plugged in for this one, but you can go ahead and plug it in and just have an expression multiplied by L. Okay. Because what we're going to do here is that now that we have this expression for the total resistance, what we can do is we can say that Q, the heat transfer rate, is just going to be equal to delta T divided by our total, okay? And then we're gonna use other expression to solve for everything else in this formula here, and then use that to solve for L, okay? Because from the problem, we can actually compute everything else here, right? And so we can compute Q because we know what the inlet and outlet temperatures for the oil are, and so we can use that to compute Q, okay? And then we can use that Q to actually compute delta T as well, right? Remember, delta T here is not just any delta T, because we're using we're doing a heat exchanger problem. This delta T is the log mean temperature difference. Okay, and so that's delta T Lm, right? And we'll actually be able to compute everything for that as well, right? And so there's still several steps to this problem still, but here's kind of the roadmap of where we're going. Okay. And so now the task is, we need to solve for Q. And then after we solve for Q, then we can solve for delta T Lm, plug all this in, and then use that to solve for L. Okay. Okay, so let's start with Q. So Q is actually pretty simple because Q is basically, the amount of heat that's required to drop, or the amount of heat the oil has to lose to drop from 100 degrees to 60. And we're given both of those in this problem. Okay. And so in the problem, they told us that the oil's coming in at 100 and it has to leave at 60, right? And so given that information, we know exactly how much heat that needs to be exchanged inside our heat exchanger, right? And so we can use this formula for Q. And so Q is going to be m dot of the oil times Cp of the oil, right? And so it's the mass flow rate multiplied by the thermal capacity, right? Or specific heat, sorry. And then we multiply by the temperature difference of the inlet and the outlet. Which we know the inlet temperature has to be 100 and the outlet temperature has to be 60. Okay. And so if we plug in the numbers for that, then we get a Q value of 8,524 watts. Okay. And then we can just plug that Q right into that equation right there. And so Q is good, okay? And so the next task that we're going to do is we're going to solve for delta T LM right here, right? And we'll be able to, we'll be able to get that just fine, you know, as you'll see on the next page. Okay, so any questions on this so far?
And the area is because the pipe, we're talking about the pipe, that's the inner pipe, never,
Exactly.
not the outer pipe.
Right. Yes. Yeah, because the inner pipe, that's the interface in between the water and the oil, and so that's basically the surface where they're going to be exchanging heat, and so that's why we use that area for that. Yeah. Okay. And so now that we have this Q value, we can actually use this Q value to compute the outlet temperature of the water as well. Okay. We can set up a similar expression for the water, right? And so the Q is also going to be m dot water times Cp water times T water O minus T water I. Okay. Okay. And so we have all this information here, especially, you know, T water I. And so we know that T water I right here, we know that this is 30 degrees from the problem. Okay. Okay. But we don't know TWO, right? And so we can use this formula here to compute WO, right? As we see that TWO, if we go ahead and manipulate this expression, is going to be equal to Q divided by m dot water Cp water plus TWI, okay? And this is equal to 40 degrees, 40.2 degrees C. Okay. All right. And so now that we have the inlet and outlet temperatures for both the oil and the water, we can go ahead and compute delta T LM.
Professor, just real quick, that Q's the Q from the previous problem, right?
Exactly, right.
Okay, just making sure.
Yeah, so basically every ounce of heat that the oil loses, the water has to gain because it's a totally closed system, right? And so, you know, that's why these two are exchanging. So that's why we can use the same Q for both. Yeah.
Professor, I had another question.
Sure. What's up?
On for the Q for the oil, you had the temperatures reversed where you started with the inlet temperature and then the outlet temperature was being subtracted, and then you switched to the next one. Why is that the case?
Yeah, it's because the for the oil, we know that one's cooling down, and so we know the inlet temperature is going to be higher than the outlet one, but the water we know is heating up, and so the outlet temperature is going to be higher than the inlet one. And so I just swapped them just to make sure that we get a positive number for both. Yeah.
Oh, okay, I see.
Yeah, so you know, it doesn't really matter all too much, but you know, if you get a negative number, you know, you can just swap it. Just because, you know, the only Q that's being exchanged is between the two fluids, and so if you get a negative, you can just swap the sign. You know, it'll all be good.
Okay, so like if the oil was increasing, let's say to 101 degrees, we'll just reverse what we did before.
Yep. Yep.
Okay.
All right. And so let's compute the log mean temperature difference, right? And so remember, the reason we have to compute this is because the temperature of the fluids is changing along the length, right? Like we already know that the oil is going from 100 down to 60, and then the water is going from 30 up to 40, right? And so, you know, it's hard to really say what the temperature difference between the two should be because that temperature difference is constantly changing throughout the heat exchanger. And so we use this log mean temperature difference as kind of like an average kind of temperature difference throughout the entire heat exchanger. Right? And so the formula for that is delta T2 minus delta T1 divided by ln of delta T2 divided by delta T1, where delta T2 is going to be equal to because this is a counterflow heat exchanger, it's going to be the difference between the outlet oil temperature and the inlet water temperature. So let me say for counterflow, we have delta T2 is equal to T oil out minus T water in, okay? And so this is 30 degrees C. Okay. And delta T1, this is going to be T oil in minus T water out. Okay. Because remember, side 1 and side 2 refer to physically the left side and physically the right side of the heat exchanger. Right? So that's why we kind of do this. But if we had a parallel flow heat exchanger, then we would do T oil out minus T oil out, and then T oil out minus T water out, and then T oil in minus T water in. But since this is counterflow, you know, the outlet and the inlet, outlet of the oil and the inlet of the water, those are in the same physical location. Meanwhile, the inlet of the oil and the outlet of the water, those are in the same location. So that's why, you know, these two are kind of swapped a little bit. Okay. All right. Okay. And so that's delta T1, delta T2. And so if we plug these in, then we get delta T log mean is going to be equal to 43.2 degrees C. Okay. All right. And so now that we have delta T log mean and we have Q, we go ahead and plug these back into this equation right here, plug in our expression for R, and we can use all of that to solve for L. Okay. Okay. So any questions on this? Okay. So let's go ahead and finish up this example here and solve for L. All right. And so let's take our equation that we had two pages ago and then manipulate that to solve for L. So we're going to have L is equal to Q divided by pi di times delta T Lm times 1 divided by Hi plus 1 divided by Ho. Okay. And we have everything in this problem. And so we have Q, we have the inner diameter, we just computed delta TLM, and we computed all the convection coefficients as well. And so you plug all that in and we get a length of 65.9 meters. And so it has to be really, really long. And so, 66 meters is not trivial, but it's, but you can do it. So that's the length that you would need for this kind of heat exchanger. Okay, so any final questions on this example before we move on?
Would like bends in the pipe change this significantly, or like if it was like going back and forth, to cut down space, how would that affect it?
Yeah, no, it's a good question, and practically that's how you would obtain this this kind of length. Because if you had just 66 meters just all as one pipe, that's hard to fit anywhere. And so the way that this is typically achieved is that you kind of coil the pipe kind of back and forth. And so as long as the outer surface of the pipe is relatively insulated, then the bends wouldn't really affect it all too much. It would affect kind of the fluid mechanics a little bit, and so the flow patterns would of course be different as you go around the bends. But if the bends weren't like if as long as it wasn't like making like an S formation, so as long as you have a relatively straight part in a bend and another relatively straight part, then I would expect the bends not to affect the calculations all too much. Because then the reason for that is if you still have a reasonably long straight section, then the flow has time to develop into its kind of fully developed state, and then the bends don't really have in those cases the bends don't have too much of an impact. Yeah.
All right, thank you.
Mm-hmm. Okay. And so that's that example. So that's a good one. And so that example kind of covers a lot of what you need to know for heat exchangers. So we kind of we kind of ran through the whole gamut there. And so we did, convection coefficients. We've used the heat transfer equation. We did the long mean temperature difference, and we used that to solve for weight. And so, when you're doing your studying for the heat exchangers, this is kind of a good one to look back on. Especially, it's going to help you out with the homework as well. Okay, and so now that we've kind of covered, most of the basic, information for heat exchangers, let's talk about effectiveness and efficiency, more specifically just effectiveness. And so this part of the notes will mimic pretty closely, our unit on fins, right? And so if you remember when we talked about fins were kind of very specific engineering devices that's used for kind of thermal management. Okay, so heat exchangers are kind of the same thing. And so, whenever you design, a device like this, you want to be able to quantify how effective it is. Because you want to be able to say, this heat exchanger is better than that heat exchanger, and you can do a calculation to kind of show that that's the case. And so, if you're the engineer that's designing a heat exchanger, you can use this effectiveness to show how good your design is. Okay, so basically, any way that you can quantify in kind of a very simple way, how well this device is going to perform, that's always going to be a valuable asset for engineering. Okay, and so the way that we define this effectiveness is through this quantity here. Okay. And the effectiveness, which I give the symbol epsilon, it's a ratio, okay? And so it's a ratio between two different things. And so on the bottom here, we have the maximum possible heat transfer in this, for this configuration. And so, theoretically, if you have these two fluids, what's the maximum amount of heat that can be transferred between them? And we'll talk about how to compute that in a second. Okay? And then in the numerator here, you have the actual heat transfer. So you have your actual device and how much heat is actually being transferred from that. All right. And so it's a ratio between, basically what you actually get and what's theoretically the maximum possible. And so you can kind of see from this that the values for epsilon here are going to be between 0 and 1, right? And so if you have an epsilon value of 1, that means basically maximum performance. And so you're basically getting the most out of your heat exchanger than that's theoretically possible. And effectiveness of 0 means that you suck and you developed a really crappy heat exchanger that exchanged no heat. Okay, so most cases you're going to be in between, between sucking and best heat exchanger ever. Okay? And for most practical cases, because it's going to be hard to achieve that maximum, your epsilons are going to be a little bit on the lower end. But this is kind of a way to kind of assess that. Okay, and so let's talk more about the denominator here, because we haven't really talked about that yet. And so the numerator here we can compute, and so we have a lot of formulas to do that, as you saw from the last example. Right? So the RoboCop cars are a no-go. Yeah, yeah, it's one way to think about it. 3 miles again. But yeah, those are not very efficient at all. That definitely would not fly. Okay. And so let's talk about the denominator here, because we've done the numerator quite a bit. And so let's talk about, what's the maximum possible heat transfer that can occur, okay? All right, let's see. What? And so just think about this problem. Let's first of all, let's say that the maximum possible heat transfer can only be achieved for a counterflow heat exchanger with an infinite length. Right. And oops. And because if you have a counterflow heat exchanger with infinite length, then that gives the ample amount of time for the fluids to exchange heat with each other. Okay. And just like we talked about last time too, that when you're comparing the performance of a parallel flow heat exchanger and a counterflow one, the counterflow one will always do better when you have longer lengths, because then because the hallmark of a counterflow is that you have kind of a consistent amount of heat transfer all throughout. And so if you have infinite length, then that basically maximizes the heat transfer that occurs. Okay. But there is a limit. And so the limit is basically that the temperatures of the two fluids can never exceed each other. Okay, so basically things cap out once the two fluids kind of reach a point where they're the same temperature. Okay, and so there's basically two ways that we can quantify this, right? And so one way is that the maximum heat transfer will occur when the cold fluid will heat up to the same temperature as the inlet of the hot fluid, or we can quantify it as the outlet temperature of the hot fluid will cool all the way down to the inlet temperature of the cold fluid. And so that's kind of a big tongue twister. And so I'll kind of illustrate that for you on the next page. But I just wanted to talk about it first before we go there. So are there any questions on this before we go to the next page?
That's supposed to say counterflow heat exchanger, right?
Yes, yes.
Okay.
I have homework on my mind, but heat exchanger out of my mouth. Yes. Mm-hmm. Okay. All right. And so max heat transfer occurs when cold fluid will heat to the inlet temperature of the hot fluid. And so that's one way to achieve max heat transfer. And the other one is, kind of the reverse. So the outlet temp of the hot fluid cools okay. All right, and so visually you can kind of think of it like this. Right? So remember we had this kind of graph before, right? And so for a counterflow heat exchanger, we have a cold fluid that looks like this, right? And so let's say that this T cold inlet and this is T cold outlet, right? Okay. And then for the hot fluid, it might look something like this. So this is T hot inlet and T hot outlet. Okay. All right. And so what you can imagine is that if the heat exchanger was kind of extended to be infinite length, then this curve right here will continue to decrease, okay, until the T hot at the outlet is the exact same as the TC inlet. Okay. And same thing on the other side too. So if this heat exchanger was extended, then eventually this curve right here will reach the same level as THI. Okay. And so once those two fluids reach the same temperature, then no more heat transfer can occur. Because remember, you need that temperature difference to drive that heat transfer. And so once those two fluids reach the same temperature, that's the maximum heat transfer that can occur. Okay. All right. And so we can put a formula on this now. And so now that we know that, we can say that Q max is going to be equal to m dot Cp min. And so the minimum value of the product of mass flow rate and Cp multiplied by the maximum temperature difference. So the maximum temperature difference is Th in minus Tc in. Right. And so that's how we compute the maximum heat transfer. Okay. Okay. So the key component of that is this value right here. Okay. And so in order to find the maximum theoretical heat transfer, you need to take the mass flow rates of both fluids, multiply it by the specific heats of both fluids, and find which one is minimum, and then take that quantity and multiply it by the maximum temperature difference. Okay. Okay. So any questions on this? I'll do an example of this later on, because I know this is the part of the heat exchangers lecture notes where it becomes kind of a mind riddle and a tongue twister. So I think seeing it in action and seeing it in example will hopefully help a lot. Okay. And so now that we can compute the theoretical maximum heat transfer, and given that we know the effectiveness, what we can do is we can use those two quantities to compute the actual heat transfer. Okay. Right. And so to find the actual amount of heat transfer that's heat that's transferred, all you have to do is just take the product of the effectiveness and the maximum theoretical one. Okay. All right. So that's easy. Okay. But now the question is, how do we actually find effectiveness? Okay. And so one way to find effectiveness is just to, if you can compute the actual heat transfer from other means. And so if it's like the previous example where you know the inlet and outlet temperatures of one of the fluids, from there you can actually compute Q actual. And then if you can compute Q actual, you can compute Q max. Then you just take the ratio, and that's your effectiveness. Okay. But sometimes you don't have access to all the temperatures all the time. So there's still a way to do it, but it involves more equations. Okay, and so the way that we compute it is kind of a couple step process. Okay, and so we need to compute these two new variables here. Right, and so the first variable that we'll compute is called NTU. And so NTU is going to be 1 divided by m dot Cp min times R total. Okay. And so NTU here stands for number of transfer units. And so it's basically a ratio of the rate of heat exchange to the heat capacity. Okay. And then the other variable that we need to compute here is CR. And CR is just going to be the ratio of the heat capacities. Right. And so CR is going to be m dot Cp min divided by m dot Cp max. And then once we have these two quantities, then there's another formula that we can plug into to solve for the effectiveness of either a parallel flow heat exchanger or a counterflow heat exchanger. Okay. All right, and so I'll show you those formulas on the next page, and then we'll do an example to kind of show you how to use it in action. All right, so there are any questions on this? Okay. And so given that you can compute NTU and you can compute CR, then you can plug those into the following equations for effectiveness. All right, so first let's write out the formula for a parallel flow concentric tube heat exchanger. So the formula for that is epsilon is equal to 1 minus exponential of minus NTU times 1 plus CR, okay, divided by 1 plus CR. Okay. Okay. And then next we have the formula for the counterflow concentric tube heat exchanger. Okay. And this is epsilon is equal to 1 minus exponential of minus NTU times 1 minus CR divided by 1 minus CR times exponential of minus NTU times 1 minus CR. Okay. And so, keep in mind that this only works for a concentric tube heat exchanger. And so there's other expressions for other types of heat exchangers, and I think some of them are in the book. And so you can look for other expressions in like tables 11.3 and 11.4. All right, so we're not gonna use those in this class, but if you're curious about them or you're working with other types of heat exchangers and for work, then you can find expressions for that over there. Okay. And so any questions on this before we do one last example? Okay. All right, so let's do one last example just to just kind of drill home these concepts and show you how to use this NTU effectiveness stuff. Okay. All right. And so let's say that we have a heat exchanger made of copper. Okay. And we'll say that it's a concentric tube, just because that's the only one that we have the formulas for. Okay. And we'll say that both fluids are water. Okay. And so the properties of those fluids are the following. Okay. And so I'll say that we'll call this inner water. Okay. So this is the water in the inner tube of the concentric tube heat exchanger. Okay. All right, so the inlet temperature for this is 50 degrees C. Okay. And the volumetric flow rate of this water is going to be 15 liters per minute. The outer water, we'll say, has an inlet temperature of 20 degrees C, and the volumetric flow rate is going to be 20 liters per minute. Okay. All right, so let's draw the geometry just so you can kind of see. Okay, so there we have the inner water. And out here we have the outer water. And since it's parallel flow, we're going to assume that they're going in the same direction. Okay. Right. So let's say that this inner diameter here is going to be 2 centimeters. Okay. And we'll say the outer diameter here is 5 centimeters. Okay. In addition to that, we can say that the inner pipe here has some thickness, and so we're going to have some conduction resistance here. Okay. And we'll say that this thickness here, we'll call it T, is 1 millimeter. Okay. And so that basically just means that the thickness of that inner pipe is 1 millimeter. Okay. Okay. And so let's solve for the following things. Right. And so first, let's compute the effectiveness of this heat exchanger. Okay. 2, let's find the total heat transfer rate. And 3, let's solve for the outlet temperatures of the 2 fluids. Okay. And so since the first thing that we need to solve for here is the effectiveness, we're going to use the formula on the previous page in order to compute that. Okay. Okay. So any questions on this? Okay. So this is the setup for the problem. So now let's go ahead and start solving it. And we're going to start with the effectiveness. All right. And so since this is a parallel flow heat exchanger, we know that the formula for the effectiveness is going to be 1 minus exponential of minus NTU times 1 plus CR divided by 1 plus CR. Okay. And so in order to compute this effectiveness, we need both NTU and we need CR. All right. And so to do that, we first need our fluid properties. And so thankfully, both the fluids here are water. And so we can, we can just evaluate the properties of water. And so in particular, since our water here is starting at 2 different temperatures, let's evaluate the water properties at kind of right in between. So it's going to be at 35 degrees C. So first we have the specific heat. And so the specific heat is going to be 4,200 joules per kilogram K. Okay. Then we have the density. The density is going to be 1,000 kilograms per meter cubed. Okay. Viscosity, we're going to say is 1 times 10 to the minus 6 meters square per second. Okay. Our Prandtl number here, Prandtl number is going to be 6. And then our thermal conductivity is going to be 0.6. watts per meter cube. Okay. All right. And so all that stuff, you can look up either in a table or in a, in something, or an online calculator. All right. And so before we proceed, we need to compute the mass flow rates of each of the fluids, right? Because we're going to need that in our equations. And so the problem here didn't give us mass flow rates; it gave us volumetric flow rates, right? And so the way that we're going to compute mass flow rate from this, we're going to take the density and we're going to multiply the flow by the flow rate, okay? But in order to use this formula, this flow rate here has to be converted into meters cubed per second. Okay. All right. And so if we do that, and so I want to make sure I finish this example. So I'll leave you guys to that. Right? And so if we plug in all the numbers for that, we get m dot inner is equal to 0.25 kilograms per second. And then m dot outer is going to be 0.33 kilograms per second. Okay. All right. Any questions on this? Okay. And so now that we have these mass flow rates, we can compute CR, right? Because CR is nothing more than just it's just the ratio between the minimum m dot CP and the maximum m dot CP. Okay. All right. So let's go ahead and do that on the next page. Okay. Okay. And so CR is going to be m dot CP min divided by m dot CP max. Okay. Where assuming that the CP is the same for both fluids, we know that this is going to be a ratio of the m dot CP of the inner fluid and the m dot CP of the outer one. And so we plug that in, and what we get is a CR of 0.758. Okay. All right. And so now that we know m dot CP min and also CR, we need to compute NTU max. Okay. My neighbor's dog is like very yappy right now. So I keep keep hearing it from over there. All right. And so remember, NTU is 1 divided by total resistance multiplied by m dot CP min. Okay. Okay. And so we have m dot CP min, and so that's that's what we just computed up there. And so now we need to compute the total resistance. Right? So the total resistance in this case, here we're going to have 3 different resistances. And so we have the resistance of the inner convection, we have the conduction resistance, and also the convection resistance of the outer fluid. All right, question. So just to clarify, m dot CP in is m dot inner times CP inner as well. Yes. Yeah. And so you just take the product of the mass flow rate times the thermal capacity that we looked up from the table. Yeah. Okay. And so our total here is going to be 1 divided by HI times area in plus Ln. Conduction resistance, and so this is going to be Di plus 2T divided by Di divided by 2 pi K of copper times L plus 1 divided by HO times outer area. Okay. Okay. And so the way that we're going to compute this is that, we have everything here. I think I forgot to give you KCU. So the thermal conductivity of copper in this case is 400 watts per meter K. Okay. Right. And then for the last thing that we need to do here is compute the convection coefficients of the two flows. Okay. And so that's HI and HO. Right. And so this is another good example here because we're going to run through basically the entire process of computing the convection coefficients based off the Nusselt number correlations. Okay. And so to do this, first thing we're going to do, so I'm going to skip a couple of the steps here just because, we are running a little bit short on time. And so the first thing I'm going to do here is I'm going to compute the Reynolds number of both of the flows, okay? And because at this point, we know exactly what the geometry is because we've done this before, and and we have the fluid properties already, okay? All right, and so let's compute the Reynolds number of the inner flow, right? And so for the inner flow, this is going to be mean velocity times the inner diameter divided by the viscosity, okay? Where the mean velocity here is just going to be our volumetric flow rate divided by the area, okay? And so we plug all that in, and what we get is 15915.5. All right. And so since this is greater than 2300, we know that this flow here is turbulent. Right? And so that's going to tell us which Nusselt number correlations that we're going to use. Okay. All right. And so next we're going to compute the Reynolds number for the outer flow, which is for flow in the annulus. And so before we do that, are there any questions on this example so far?
The V is a V, not viscosity.
That is viscosity. Yes.
Okay.
The dog's never been this yappy before. It's can you guys hear the dog at all or no?
Bits and pieces.
Okay. Yeah, it's never this loud before. I wonder what's going on. I'll check
Give
it
the
out.
dog
After.
some NyQuil laced ham.
Yeah, maybe I'll suggest that to my neighbor. Okay, and so now that we know the Reynolds number of the interior, let's compute the Reynolds number for the annulus. All right, and so for the annulus, remember, we have to multiply by the hydraulic diameter because that's that's what we typically do for this for these problems. Okay. And so just like before, we have times hydraulic diameter divided by viscosity. Okay. Where again here is going to be the Q divided by A times DH divided by nu. Okay. Where remember for the annulus, we have to take just the area of that annulus. Right? And so A in this case is going to be pi divided by 4 times outer diameter squared minus the inner diameter plus 2 times t squared. Okay, because remember our inner pipe here has some thickness to it, right? And so we need to account for that thickness when we compute this area. And so the area is going to be the outer circle, where the outer circle here has a diameter of DO. Okay. And then normally we have this inner diameter DI right here. But that's not the inner diameter of the annulus, because remember we have kind of a very thin layer of copper around that, and the thickness of that copper is 1 millimeter. Okay, And so that diameter there is going to be basically di plus 2t. So that's why we kind of use that. Okay. All right. And so we plug all that in, and what we get is a Reynolds number of 5,835.68. Okay. And this is also turbulent. Okay. And so since both of these regimes are turbulent, they're actually going to follow the exact same Nusselt number correlation. Right? And so we're not going to use the table for this Annulus flow because it's that table was only for laminar flow. Right? And so since we're turbulent here, the Nusselt number for both cases is going to be 0.023 times the Reynolds number to the 4/5 times Prandtl number to the 1/3. Okay. All right. And then from that we can find the convection coefficients by multiplying by thermal conductivity divided by diameter. Right. And so for the inner water, what we get is HI is equal to KF divided by DI. Okay. And I'm just going to plug in this expression for the Nusselt number correlation here. So this would be 0.023 times Reynolds number to the 4/5, Prandtl number to the 1/3. Okay. And so we plug in all the numbers for that, and what we get is a convection coefficient of 3,250 watts per meter squared K. Okay. And then for the outer diameter, we can do the same thing. So for the outer fluid, we have KF. This time we're going to divide by the hydraulic diameter because that's what we do for the for an annulus. Okay. Times 0.023 Reynolds number to the 4/5 times Prandtl number to the 1/3. Okay. And we plug all that in and we get 870 watts per meter squared. Okay. All right. And so now that we have all of that, now we can compute the total thermal resistance. Okay? And then once we have the total thermal resistance, we can use that to compute the NTU. And then once we have NTU, then we can use that to compute effectiveness. And so it's going to be just a cascade of plugging things into the formulas that we've already established for this example. Okay. Okay. So any questions on any of this so far?
When you were doing the convection coefficient for inner versus outer,
yeah,
the Prandtl number, doesn't it change depending on whether the fluid is being heated or cooled?
So yeah, so that's that's a good question actually. So yes, actually yes, I did miss that point. Thank you. And so you're right. And so the exponent on the Prandtl number does change depending on if it's being heated or cooled. And so for the inner one, because the inner one is being, I think the inner one's being cooled, right? Or that one's being heated. The inner one's being cooled. And so we're going to use a exponent here of 0.3. And then for the outer one, we have an exponent of 0.4. Yeah, thanks for catching that. I totally missed that in that example. Yeah. Mm-hmm.
Professor, quick question. For area, where you have DI plus 2T squared.
Yep.
Will the T ever be given, or is that just supposed to be DH?
So that's so the T is given in this problem. So the T is is the thickness of that inner pipe, and so that's basically this distance right here. So it's really small, and so I kind of was really messy at the beginning of this problem, but that T for this problem is 1 millimeter. It's right here.
Gotcha. Okay, thank you.
Yeah. Yeah, so that's given to you. So most geometric quantities will be given to you. If not, then something you solve for. But usually for these heat exchanger problems, I have you solve for the length, not for the diameters.
And then we could leave that as millimeters or changes in meters.
Yeah, so definitely change that to meters. And so make sure when you're computing areas and stuff like that, you convert everything to meters.
Okay, thank you.
Okay, and so now that we have the convection coefficients, let's go ahead and plug in for and compute for total resistance. And so the total resistance is going to be 1 divided by HI times the innermost area. So this would be pi di times L, okay, plus ln of di plus 2t divided by di divided by 2 pi KL, and this is K of the copper, okay, plus 1 divided by HO times the area where the outer fluid's connecting to the inner one. So this is going to be pi times di plus 2t times L, okay. And I'm not sure if I gave it to you, but the length of this heat exchanger is 1.5 meters. Okay, I think I forgot to mention that. Okay. But that's given to you in this problem as well. Okay, and so we can plug in basically everything for this, and we get a total resistance of 0.14325. Okay, and then now that we have total resistance, we can compute NTU, where NTU is going to be 1 divided by m dot Cp min times R total. Okay. And then what we get is 0.0665. Okay. And then now that we know NTU, we can compute effectiveness. Okay. And effectiveness is 1 minus exponential of minus NTU times 1 plus CR divided by 1 plus CR. Okay. And this is going to be 0.062. So this is not a very effective heat exchanger. So we're not going to get very much heat transfer out of this. Okay. And so that was kind of a lot of steps kind of in one. But basically, the way to sum this up is once you have the total resistance, then you can compute NTU, and then NTU is used to compute the effectiveness. Okay. Well, remember, this formula for effectiveness depends on whether you have a parallel flow or a counterflow heat exchanger. And since this is a parallel flow one, then we use this formula. Okay, so any questions on this? Okay. All right, so we're almost done. And so now that we have the effectiveness, everything else kind of just falls into place. Okay. All right. And so now that we have the effectiveness, we can compute the actual heat transfer rate for this heat exchanger. Okay. And so remember, Q actual is equal to effectiveness times Q max. Okay. We just computed effectiveness, and so let's go ahead and compute Q max. Okay. Right. And so remember, Q max is going to be equal to m dot Cp min multiplied by the biggest temperature difference in our heat exchanger. And so the biggest temperature difference is always going to be THI, or the inlet temperature of the hot fluid, minus TCI, which is the inlet temperature of the cold fluid. Okay. All right, and so we perform those calculations, and what we get is a heat transfer rate of 1970 watts. Okay. All right, so not that much. Okay. And then now that we know the actual heat transfer rate, we can use that to compute the outlet temperatures. All right, so I'll do one just because we're just about out of time, and then you can use that. You can use basically the same thing to solve for the other one. Okay. All right, because we know that Q actual is equal to m dot Cp times of the cold fluid. And so I'll do this for the cold fluid. Okay. T cold out minus T cold in. Okay. And so what we have is T cold out is equal to Q actual divided by m dot Cp of the cold fluid plus Tc in. Okay. And then what we get is an outlet temperature of 21.4 degrees C. Okay. And so you can see here, we barely have any change because the inlet temperature of the cold fluid was just 20 degrees C. And so we can see we've only changed the temperature by 1.4 degrees C, which is not that much. And then you can repeat the same basically repeat the same formula right here, except replace everything with the hot fluid. Okay. And so if you basically replace this with hot, replace this with H, replace this with H, then you can find the outlet temperature of the hot fluid as well. Right? Okay. All right. Any final questions on this before we wrap up for the week?
When you were computing Q actual, why do you use m.cp minimum and not max?
Yeah, that's a good question. So the reason we use minimum is because one fluid, you can almost think of it as like one fluid is going to be limiting the total amount of heat transfer to the other one, right? And so the fluid with the and this is kind of a good example because both fluids have the same CP, but the total amount of heat transfer is going to be limited by the lower mass flow rate because that fluid just going to have less heat transfer than the other one. And so it doesn't really matter how much we flow the other fluid, but we're limited by how quickly we're moving that minimum there. And so it's Q max in terms of the temperature difference, but it's still limited by the mass flow rate of the slower fluid. All right. Any final questions on any of this? Okay. All right. So that's all we got time for today. And so thank you guys for tuning in. I'm going to put up a poll probably sometime later this evening so you can vote on the topics from the convection unit that you feel most uncomfortable with. And then Friday, I'm going to record the review video for midterm 2. Okay. All right. So thank you guys for tuning in today. Hope everyone has a good weekend. And I'll see you guys next week.
Thank you, Professor.
Thanks, guys.
Professor, I did have a quick question.
Sure. What's up?
For the compute effectiveness for the final answer.
Yep.
That is 1 minus NTU times 1 plus CR.
Yep.
What's the EXP part?
EXP is exponential. And so when you have exponential of x, this is the same thing as e raised to that x. And so this is taking 1 minus e raised to the minus NTU 1 plus CR. And so another way to write this would be, let me write this on the next page. Or the next page. All right, and so 1 minus exponential of minus NTU times 1 plus CR. All right, another way to write this would be 1 minus e raised to the minus NTU times 1 plus CR. Yeah.
Gotcha.
So since things get a little bit hard to write when it's e raised to stuff, and so that's why we use x to kind of shorten that or to make things easier to read.
Gotcha. I was thinking of that, but I just wanted to clarify just in case I missed something.
Oh yeah, definitely good to clarify that.
All right. Thank you. Have a good one.
Thanks, you too. Ethan, did you have any other questions? Okay. All right. So if there's no more questions, I'm going to go ahead and sign off.